We're going to talk about two approaches to numerical differentiation, which is finite differences. And the two things that I want to make clear are the difference between a situation where you have a known function, that's a Python function which implements some kind of calculation where you can use two or more function calls, and in particular you can pass an arbitrary value of x to that function. And then the other approach is where you have an unknown function, an example where the function is represented only by values on a grid. So this is something where you're going to be calculating successive values of some function. And a good example, which I'll return to in a minute, is the Schrödinger solver that we've looked at in another video, where we're varying the values of the wave function on the grid and then calculating the energy by numerical integration. And in that case, the wave function psi itself doesn't have any known functional form, and so we have to do a differentiation on a grid. So let's think first about known functions, and I've written here the finite difference formula, the forward difference, first order finite difference formula for the differential, where you've got f of x plus delta x minus f of x divided by delta x. And the key point here is that we can set the accuracy by choosing the value of delta x, and we can specify essentially any value we choose for delta x, because we're going to be performing calculations of f, and we can choose any value that we want. So let's write a little function that does this. We're going to call it evaluate df dx. We're going to pass it f, the function x, and dx. We'll put in a doc string which basically says forward evaluate forward difference of f at x using spacing dx. We'll put in the inputs. F is the function to be differentiated. X is the point at which to evaluate df by dx, and that can be an array if we want to, and dx is the step size. And the output here is simply df dx. It's the forward difference, same shape as x. So we're going to define f underscore x. So we're just going to store that as the function of x. We're going to define fx dx. It's just going to be the function of x plus dx. And we'll define the gradient as being fx dx minus fx divided by dx. And you can see that that's just a simple translation of this formula into code. And we'll then return the gradient. We could, of course, put in some checks. We could make sure that dx isn't 0, this kind of thing, but for now we'll just leave that as something fairly simple. Now, let's I'll do some examples in a moment, but let's now just consider the question of unknown functions. What are we going to do here? And here I'm just going to copy a little bit of text that I've prepared already to speed things up. What we're doing is we're doing this. We're saying that df by dx at xi, where xi is going to be a point on a grid, is given by f of x I plus 1, i.e. the value at the next grid point, minus f of x at I, that's the value at this grid point, divided by delta x. Of course, delta x is the grid spacing, and we're assuming that xi is given by x0, some starting point, plus I times delta x. So this is a way of representing a function on a grid. We don't need to know how the function is evaluated. And in this case, the choice of delta x is set by our grid spacing. And this is a more stringent requirement. So in the previous example, we could set any value of delta x we wanted to. In this example, the value of delta x defines the grid spacing, which is going to impact on things like storage and on calculation time. So it's not something we can set freely. So let's just define a new definition here. So we'll say evaluate df dx grid. And again, we're going to have f, but we're going to have dx here. And in this case, actually, I'm just going to change that to f underscore arr, meaning f as an array. Okay, we'll put a doc string in again. Again, we'll say evaluate forward difference for array of values f underscore arr on a grid with spacing dx. And hopefully that makes it clear the difference here. This is only used where we have an array. So the inputs are given as f, which is an array of values. It's not a function. Dx is a grid spacing for the array. We could, of course, pass in the array x, but we don't need it. And then the output, let me just scroll up, is going to be df dx, which is going to be an array of gradients on the grid again. Now we could do this with a sort of a slow approach. So let me actually just put a comment here just to make this clear. Using the slow approach, then we would say df dx is numpy.zeros like of f. So what that does is it creates an array full of zeros which has the same shape as f. But remember, it's going to be called f underscore array. And then we're going to iterate. So we'll do for I in range, let's say length of f minus 1, because we're going to have to think about what happens at the end of the array. We'll come back to that in a moment. And we say that df dx of I, at grid point I, is equal to f at I plus 1 minus f at I divided by dx. And again, you can see that this is exactly translating this formula here into code. And notice the difference between the two. In this case, we've got tabulated values. In this case, we've got a function call. That's the slow approach. Of course, the fast approach we want to use is using NumPy arrays. So we're going to put this in. I'm going to comment out the slow approach when I've done that, just so that we can make it faster. And here would say fp for f plus. When I say f array p is numpy.roll of f array comma minus 1. So that's shifting. Excuse me. That's shifting it forward. And now we say that df dx is f underscore array p minus f array, and I've just noticed that my f's up here should be f arrays. I got into thinking of it as just f. So coming back to the fast approach, we do the numpy.roll, so we shift the entire array by 1 to create a new array f array p, and then df by dx is just f array p minus f array over dx. So that's calculating this formula here, where you're taking the difference between successive grid points, but doing it for the entire array in one go. Now, because we're doing that, we have to think about the final point, which isn't defined. So we'd say that df dx of minus 1 is equal to 0. There are other conventions you can follow, but you just have to be careful about that. And then we return df dx. And I'm now going to go back and comment out the slow approach. I put the slow approach in just as a simple illustration of how you would do it, but the NumPy way is much, much better. So let's think about a known function demonstration, a way of demonstrating this known function. So we're just going to do something very simple. So what we'll do is we will set up an array of possible spacings, numpy.log space. Oopsie, I can't type suddenly. -1 to -5, comma 5. So that's going to give 10 to the -1 through 10 to the -5 for the spacing. I'll choose the value x is equal to 1.0, and we will use just a simple sign. I'm going to say sign diff dx. In other words, the differential of sign using dx is just evaluate df dx of numpy.sign. That's our known function. X, which is our position in space, and dx, which is our set of values. And we can run that. And now let's plot this. So we have a log plot, and I'm going to give it dx, and then I have to use numpy.abs because I can't take a log plot of a negative number, and I'm going to take the sine diff dx, the one I just calculated, minus numpy.cos of x, which I know is the exact result. So I'm just plotting here the difference between the approximate and the exact results, and I'll plot it with circle with points and lines. And here's our plot. Okay, so you can see that, as expected, the relationship between dx and the error is linear, which is the same as saying that it's first order. So let's just put some axes on here. X label, label should be dx, plot.y label should be error in differential, and plot.title is characterizing forward differential, forward difference. There we go. So there's our graph for a known function. Now, okay, this is a particularly banal or simple explanation because numpy.sine is something where we know the exact result. I'm doing that because we have this example, but it illustrates the point. So now let's also turn to the unknown function. Again, I am just going to use an array of sine points. Actually, before we do that, let me just demonstrate something else here, which is the following. Let's create a set of x values, a set of points on a grid, which are going to be widely spaced. So I'm going to go from 0 to 2 pi, but I'm going to need to take 11 points. Okay, I'm going to choose a particular dx, let's say 10 to the minus 3, and let's do the full sine difference. So that's evaluating the error in the sign for a particular value of dx, but at a number of different points. And that's going to be evaluate df dx, and we're going to do it again, numpy.sine. As the x values, I'm going to give this little array x vals, and I'm going to pass it this dx. Now, why have I done that? Well, so basically now I'm wanting to characterize the accuracy of the differential at different points along the function. So let's plot out our x values. Oops. X vals, comma, sine diff. Why is that suddenly doing this? Oh, because it thinks it's a markdown code cell. Okay, the tab offers completion, but only if you're in a coding cell. Okay, so what we're doing here is we're plotting the difference between our approximate sine, that's this full sine diff, actually, so I've put the wrong thing in here. And I'm going to put it with circles out of line, and let's just see what that gives us. So this illustrates the fact that with this technique, we have a known function. We're using the numpy.sine function, but we could use any other function. It could be the energy of a wave function for a particle in a box, or lots of other things. And we can pass in different values of x, and because we have a known function, we can specify the value of dx that we're using to do the differential, and we see that the error is well bounded. So the error in the sign is it's down at 10 to the minus 4 in this case, which fits quite well with the graph up here. You see a dx of 10 to the minus 3 gives us an error of a few by 10 to the minus 4, which is very consistent. So let's just put some labels on here. Plot.x label should be x, and plot.y label should be finite difference error. And we'll put a title, which could be the same as a figure caption, where we're going to say finite difference accuracy. Oopsie, finite difference, not df, accuracy at different points, different x points, maybe. This, of course, this graph here is not something that we could do in the same way when we've got an unknown function. So let's now go back to this unknown or grid-based approach. So actually, that's a better name for it. We'll call it grid-based demonstration. So let's start with a large number of points. So a large dx. N large dx is going to be, let's say, 61 points. So this is going to be a grid. I'm going to create a set of x values, large dx. It's going to be numpy dot linspace from 0 to 2 pi, and we're going to use n large dx. Let's create a value of dx. Dx large is just 2 times pi divided by n large minus 1, because remember you're going to have the endpoints there. Let's print that out. We use a formatted print statement, and we'll just say large spacing is dx large. And we'll create an array, so test array large dx is going to equal numpy.sine of x vals large dx. So that's just our set of array points, and then our grid-based differential for a large dx is going to equal evaluate df dx using the grid. And in this case, I'm just going to remind myself how that works. Okay, I pass it an array, which is going to be our test array, and I need to give it a dx. So that's going to be dx large. Now let's do small value of dx. So let's actually put that comment at the beginning here. Large value of dx. So we're going to need to specify more points. So let's say n small dx is going to equal, let's say 601. Let's do a bigger, let's say 6001 actually. And then we're going to do exactly the same thing. X val small dx is equal to numpy dot linspace of 0, 2 times pi. Numpy dot pi, not just pi, that's not defined. Comma n small dx. Dx small is going to equal 2 times numpy.pi divided by n small dx minus 1. And we're going to print formatted, and we're going to say small spacing is dx small. We're going to set up a test array. Okay, I shouldn't have used a tab there. I want a new variable here, numpy.sign of x vals, and I can use a tab here, x vals small dx, so that's creating the array of values on a finer grid, and our grid differential. Again, I shouldn't have used a tab. Dx is it's evaluate df dx grid of test array small dx, comma dx small. Okay, so that's our calculation, and we see that the large spacing is 0.1, the small spacing is 0.001. So let's just plot the x values, large dx, and we'll do the grid difference large dx minus numpy.cosine of the x values, because we know that cosine is the analytic derivative, and this is just something to characterize what's happening here. And we'll do the x values for the small dx, and we'll do grid difference at small dx minus numpy.cosine of the x values at the small dx. And if I run that, what do we see? Okay, well, so we see that we've got 2 lines. I haven't put any labels on, so let's put the labels on. I mean, it's pretty obvious which way around they are, but pretty obvious is never a good scientific thing. So this is label. If we've put a format string here, then we can say dx is equal to, and then put dx large. And then for the other one, we can do label is equal to formatted, and then we put in here dx is equal to dx small, and close the quote, and then do plt.legend so that we actually display it. Okay, so we now have the legend. We could go back and tidy up the formatting. So the blue line is for the large dx spacing 0.1, the orange line is for the small dx spacing 10 to the minus 3, and we can't really tell the difference on this. So what do we want to do? We want to put this on a logarithmic y plot, so plot.semilog y, but notice we've got negative and positive errors, so we're going to have to do an absolute. So I do numpy.absolute of this, and I'm going to put a numpy.absolute in here, and I'm going to change my plot to a semilog y. What do we get? Okay, so the semilog y doesn't own, the semilog y does take a label, but numpy.abs doesn't take a label. I put my bracket in the wrong place. There we go. Now we can see what's happening. We can see that the error for the large dx is up to around 5 by 10 to the minus 2, and it's 100 times smaller for a dx, which is 100 times smaller. So this is interesting because it shows us that for this grid-based approach, the error will vary where we are, but of course it's still going to be approximately linear as we would expect. So if we make dx 100 times smaller, the error drops by 2 orders of magnitude. Let's tidy this up. Let's put a grid on here. and we'll put an X label, X, we'll put a Y label of error, and we'll put a title comparing grid-based differentiation, finite difference. Okay, so what have we learned? We've learned that there are two ways of thinking about coding up numerical differentiation. Of course, there are lots of different ways of doing it, but these are the two key ones. The first case, you have a known function. So that's the function when you create your differential, you're going to use a known function f, which will be a Python function. And in this case, the choice of dx is entirely your choice. You are just doing the calculation. You can calculate at a single point x, or of course you can pass in an array of values. But in this case, the spacing between grid points, if you pass an array in, is not related to the delta x, the step used for the differential. That's the key point. In the case where you've got an unknown function, which, for instance, if we think about the Schrodinger solver that I've already talked about when we're doing the second derivative, we'd have. Now, this is interesting because let me just show you what happens. Here's our starting point. We have a little Gaussian we put in for the first place. If I just force it to only do 10 iterations in its calculation and then plot the wave function, let's not plot the analytic just for now. Here is our wave function where we've been doing some kind of numerical optimization. So that is no longer a known function. It is a set of points on a grid. And this is a situation where we can only do the kind of grid-based differentiation. So there's an example. You can find the notebook for that on Moodle. I'd also put it in my GitHub directory if you're looking at this on YouTube. So in the case of the unknown function where we have a function tabulated on a grid, then the only way that we can calculate the differential is using successive grid point values. Of course, if we were doing a center difference, we'd use 3 grid points, but the same point is made here. And the spacing, delta x, is defined by the grid, not by our decision on how accurate we want our differential to be. Of course, when setting the grid spacing, one thing you have to take into account is accuracy, but it'll have various other inputs. So in this case, instead of doing a differential where we do f of x plus dx minus f of x, we're using successive array elements. And I showed that in this slow approach, which I then commented out because we want to use NumPy arrays. For the known function, we picked a single point in space and we characterized the effect of changing the grid spacing. And we see that it's nice and straight and linear, and it's very easy to do that. We then looked at what happened when we take a set of points in an array, so points on a grid, with what is actually a very, very coarse spacing. But of course, the spacing on the grid has no bearing on the accuracy of the differential because we set the differential using this parameter. For the grid-based demonstration, we have our function at points on a grid, and we looked at both a very coarse grid and a rather fine grid, and we saw that the error that we get depends in very, very linearly, as we'd expect, on the spacing of the grid. But notice that in this case, the grid spacing is the same as the differential grids, the step used in the differential. That's really what I wanted to say. It's important to understand the difference between these two different approaches to differentiation when we're doing things numerically.